Alright, our next major unit is on rotations, and before we can of course talk about the dynamics of rotation, we have to describe its kinematics. We have to figure out how to describe how things move in a rotational sense. So, if I were to ask you, where is the purple dot? There's several things you could answer, but maybe the most easily, or the most likely thing, is to say that it's 2 units from the origin at 30 degrees as marked. And if I asked you where is it now, you'd probably say 2 units at what looks to be 75 degrees. Clearly the dot has moved, but it's not convenient to specify this motion as motion with x and y components, where you say that it moved, over some amount and up, because it's moving along a circle. So we're constrained to the circle. We'd like to take advantage of that constraint, and we're going to discuss these kinds of motion. Like the earlier work in kinematics, we'll need to specify an origin, but now we'll also need to specify a reference axis as well. We usually use the plus x-axis, but that's not strictly required. So you might, if you look at that picture, we have a circle, and we were measuring all our angles from this thing, which was defined to be 0 degrees. It is a convention in both math and science that, barring anything else, counterclockwise is considered plus theta. So moving this way is plus theta. If you wonder why that kind of strange convention, it comes down to the idea that we have a right-handed system where we write x and y, and we move one into the other. We will be measuring our angles in radians, which says that the angle is going to be defined as the arc length taken along a circle when the circle's radius is known. And we define our angle to be that arc length over the radius of the circle. Right, the distance measured along the circle. The advantage of this is that it scales. If we had taken a smaller circle, we would get a smaller arc length, but we'd have a smaller radius proportion, so we'd get the same angle. Or put a different way, all circles are similar, and this allows us to talk about locations on them without regard to how big they are. You might ask, why do we measure in radians? And the shorter answer is calculus. The somewhat longer answer is, when measured in radians, the derivatives of trig functions are simplified. In all of the units of measure, we introduce correction factors, and they're just annoying to track. This happens quite a bit in calculus. There's also, why do we work in the natural base e? Because the derivatives of the exponential and logarithmic functions have no correction factors in base e. It makes your life easier, even though at this moment it probably doesn't feel that way. One useful feature of radian measure is that we can invert the definition. Given a radius and an angle, we can easily compute the distance traveled along the circle. We can find the arc length as r times theta. We can see, since once around the circle we've traveled one circumference, it should be relatively obvious that theta around once around is the circumference, 2 pi r, but then divided by r, or 2 pi. In other words, going around the circle once increases your angle by 2 pi. As an aside, the angle around a circumference is 2 pi. It's not 2 pi something, not 2 pi degrees or whatever, not really even 2 pi radians. It's a pure number with no units, right? And again, that comes down to theta is a distance over another distance, no units. You'll often hear people quote angles in radians, and we do that because people are used to there being something attached to an angle measure. Oh, that angle is 75 degrees. And so it sounds a little weird to have it nakedly, no, this angle is pi over 7. People want there to be another word to follow on, just like degrees. So by convention, we tack on the word radians to say that we're in radian measure, but really the radian is not a unit. It's just a verbal convenience. It doesn't play any role in the math. What that means is that radians don't respect unit analysis because they're not units. So this thing what we've done all year about checking the dimensions of things, we have to be careful because radians can kind of come in and go out of that, and it does not affect the validity. All right, so which particle here has an angular position of 5 pi over 2? We start off by saying 5 pi over 2 is 4 pi over 2 plus 1 pi over 2, or 2 pi plus pi over 2. Why do we do that? Because we start on the positive x-axis and we go around 2 pi. Well, that's all the way around once exactly. And then we have left over pi over 2, which is 1/4 of the remaining distance. So we end up as marked here, A. All right, there are rotational analogs to the kinematic variables we explored earlier in the year. For instance, instead of linear displacement, a change in x, we'll talk about angular displacement, a change in theta, and we'll write it the same way we might expect as delta theta. Here we have something undergoing uniform circular motion, and so delta theta is the same no matter what time interval we pick. We can see that we have two different angular displacements per second. So we have something which goes through, in the first 5 seconds, it goes through pi over 2, whereas this one goes, in the same time, goes through pi, or twice as far. All right? So it experiences twice as much angular displacement on the left in the same amount of time. So now we're going to define something called angular velocity, which is symbolized by omega and measured in radians per second. Please note that this is the Greek letter omega. It's not a curly W, and don't call it that. It makes you look a little silly. So omega would be defined as delta theta over delta t, and this is an exact analogy to how v was defined as delta x over delta t. Then we can say that an object which is traveling in uniform circular motion will have an angular velocity that is constant. All right, ball rolls around a circular track with an angular velocity of 4 pi radians per second. What is the period of the motion? Well, remember that the period t was defined as time for one repetition. So in this case, it should get us that delta theta is 2 pi, because that's the angle in one repetition. We know omega is delta theta over delta t, so it's going to be 2 pi over the period. Hey, you might remember we had that earlier, actually. Way back when in oscillations, we talked a little bit about it accidentally, and now we see that was entirely an accident. So now we can say that the period is 2 pi over omega, so it's 2 pi over 4 pi radians per second, and we get 1/2 seconds. And notice that this radians per second went away. That we have the radians per second became 1 over a radian per second became just seconds, not seconds per radian. That's what I mean about not respecting dimensional analysis. All right, let's find omega for this particle. Let's answer in radians per second and in multiples of pi. In other words, we generally don't multiply through by the pi until we're going to take actual physical measurements because we don't have meter sticks calibrated in pi. All right, so we can take omega is delta theta over delta t, and we could say that it goes through pi over 2 radians in 5 seconds. So that is pi over 10 radians per second, or the way it was phrased here, 1/10 pi radians per second. Somewhat annoyingly, people use other units here. Although we like to measure in radians because they're pure number and they're what calculus respects, people often give omega in degrees per second, which is awful, or in RPM, which stands for revolutions per minute. One revolution, of course, is just once around, so we can just say one revolution is 2 pi radians. You'll also see RPS, which is revolutions per second, or other variants. But be careful, because many of the formulas that we'll derive depend on being measured in radians, not in degrees or in revs. Here's where this all pays off for us. Because math derives meaning from form, not from the intrinsic symbols, we can reason from the fact that angular velocity is defined in terms of angular position in the same way that linear velocity is defined in terms of linear position. Specifically, we can say on an angular position versus time graph, the angular velocity is the slope. If I have a graph of theta versus t, then this slope is omega. So the stuff we did way back in the fall about all the kinematics involving graph things or involving the equations we derived from the graph things, those will all still hold. We don't have to learn them again. We don't have to derive them again. We can just jump to using them analogous. So here we'll say find omega for this roulette ball, answer in terms of radians per second in multiples of pi. So we would say omega is the slope, which looks to be, I'm going to take this point and that point. So 4 pi radians in 1.2 seconds, which is 40/12 pi radian per second, which is 10/3 pi radians per second. All right, here it says sketch the position curve for a wheel rotating at a constant pi over 3 radians per second. So I want to draw a line that has pi over 3 as its slope, which is hard to do. Pi over 3 is something like 1, but a little bit more. Instead, I'm going to say that omega is going to be, omega is delta theta over delta t. So delta theta is omega delta t. So in, let's say, 5 seconds, we'll get pi over 3 radians per second times 5 seconds. So we get something like 5 pi over 3 radians. So we end up at something like a little bit more than 5, like 5.24 or something like that. So we'll end up there, and we know that it's a straight line. Right? It's a line because omega is constant. So the slope is constant. All right, so far we've been talking about analogies. Theta is like x, and omega is like v. But in addition to that analogy, there is also a direct relation between the linear velocity and the angular velocity. In other words, for something which is going around in a circle, we know that it has a linear speed, and that should be connected to its angular speed. But it's pretty easy. The distance it tracks out is r theta, so the change in arc length is going to be delta of the change in r theta, but r is a constant, it's on a circle, so that's really r times delta theta. And if we then divide by delta t, delta s over delta t, how fast we're going around the circle, is r delta theta over delta t, which is r, well, just grabbing the r out front, so we have r times delta theta over delta t, but that's omega. So we end up that v is r omega. That if I know the angular speed and the radius, I can figure out what the linear equivalent speed would be. Notice that this is only true if omega is in radians per second. It doesn't work otherwise because this goes wrong otherwise. We can only say that theta equals, that s equals r theta. This is only true when theta is in radians. All right, the diameter of an audio CD is 12 centimeters. The disc spins at 540 RPM. What is the speed on a point of the edge of the disc? And answer in meters per second. There's a little note here that says, remember that RPM is revolutions per minute. So RPM, 1 RPM means it goes around exactly once each minute. So RPM is a unit of frequency, and therefore also angular speed. In other words, this is omega. Here we can see the calculation worked out. We start with the idea that v is r omega, that the speed of a point on the edge is going to be r times its distance, its angular speed. So it's going to be 12 centimeters times 540 RPM, which is a true answer but not useful because we want meters per second. So I've got to convert the centimeters to meters by saying 1, it's the radius. Actually, sorry, there's a bit wrong here. This is 1/2 of that. The radius is actually 6 centimeters, so we need that in here. Converting centimeters to meters, no big deal. Then we've got to convert RPM to radians per second. So rev per minute multiply, times 2 pi rads per there are 2 pi radians per 1 revolution, and there is 1 minute in 60 seconds. And if you grind all of that out, you get 3.39 meters per second. All right, this is the angular velocity graph of a wheel. How many revolutions does the wheel make in the first 4 pi seconds? So we want this entire region of time, and at first it's spinning up. Eventually it's spinning at a constant rate. But we happen to remember how velocities are connected to displacements on graphs. So we're going to use that it must be that delta theta is the area trapped. Because on a velocity graph way back when, we knew that the area trapped by the velocity curve gave us the displacement delta x. Here our velocity is angular, so we'll get delta theta instead. And so we can look at it as 2 regions. This region gets 2. It's 1/2 times 2 rev per second times 2 seconds. And this region gets 4 because it's 2 revs per second times 2 seconds. And so delta theta is that, which is 6 total revs.